Uh, Hi everyone, good morning guys. Good morning. Just give me 1 minute. I'll just arrange the setup here. Just 1 minute, guys. Yes. So in the last class, we have discussed about PCA. Mm, yeah, in the last class, we have discussed about PCA model, right? We have understood few important points about PCA. Let me just quickly recap that, guys, to everyone. PCA, which stands for Principal Component Analysis, right? And all these principal components are the new dimensions, right? Which are again linear combination of old dimensions, which are linear combination of old dimensions, right? So this is what the first point that we understood. And then the next important point is it is used for dimensionality reduction. Okay, because there is a problem called curse of dimensionality. That is why this dimensionality reduction model will be used, which is PCA. Okay. And another important point is that it uses all the basic linear algebra, right? The most important concept used is eigenvector. And what is eigenvector? Can anyone tell me how do you define an eigenvector? Anyone, guys?
Eigenvectors are nothing but you need the definition or the formula.
Definition.
Okay. Eigenvectors are nothing but even after the transformation, the direction remains the same.
Hmm.
So when we have the original features, after we are going to transform it, I mean like capturing all the variance using the covariance,
Yeah.
will be finding the new dimensions. The new dimensions are nothing but the principal components, which are nothing but the eigenvectors. So,
Right. Okay.
mm,
Okay. Correct. So just to reframe what she was saying, eigenvector is that vector whose direction won't change. Okay, but magnitude may change. Right? Magnitude may change. There are two properties for any vector, which are direction and magnitude. Right? So with respect to those two properties, eigenvector is that vector whose direction won't change, but magnitude may change. An eigenvector is always with respect to a matrix, guys. Right? Please remember this, never forget. Eigenvector is not a standalone separate concept. It is with respect to a matrix. That is, if you look at the formula, matrix into vector is equal to lambda into vector. Right? Very simple. So this is an eigenvector because it is satisfying this formula for, and this is an eigenvector for this matrix of matrix A, right? If I have another B V2 is equal to lambda V2, then let's say this. So V1 is eigenvector for this matrix only, not for B. Right? B is another matrix for which you have another eigenvector called B2. Right? It's always with respect to a matrix. And we were using this basic linear algebra concept to be able to find the new dimensions which are covering the majority of the variance of the data given, right? So, uh, yeah, and the A we will take for A in PCA model is covariance of the data, right? Because I need that vector, I need the vector whose information is similar or same as A, right? And I need to take variance only over here because I want the model to cover majority of the variance, right? See, if I have many dimensions like this and the data is spread like this, okay, I have many dimensions like this. But if I take this and this, I could have very well expressed this data using these two dimensions. That way, dealing with two dimensions is much easier, and I can build a model like linear regression or logistic regression on just two dimensions. It is easy to build. Okay. So if you take this out, I can express the data in this particular new dimensions now. I will say it as dimension one, or oh, sorry, I will say it as PC1, PC2. But what are these? How to find these? These are obviously covering the variance of the data very well. That is why I have these as the dimensions, right? So I'm not having this as a dimension or this as a dimension here, and the data is here. No, that is useless. I'm having something like this, where it is covering the variance of the data. So the initial variance is available in all of these dimensions, right? But there exists some vectors in the universe which will actually cover the variance of the data very well. And we have to identify those vectors, right? And that is why we are seeing vector whose direction is same. That is, let us say this is what this is one direction of the variance from the original data set, right? Original data set. And I am also getting that vector whose direction is this way only. And variance is there in this side also. As you can see here, here to here, data is spread. And here to here also, data is spread, right? So in two directions, I have variance, let's say. Therefore, I will have vectors in these two sides. But the magnitude can be little different. That is okay. That is okay, right? So obviously, I need to identify a vector where the information of the covariance matrix is present. So that is why I will be taking will be a covariance matrix of the data set, but not the data set itself. A is not the data here. A is covariance of the data here. Okay, this is what we have learned. And we have also seen principal component is nothing but linear combination of original features. For example, if I get PC1 as 2, 3, 5, 3, 1.5, then PC1 will be 2 into x1 plus 3 into x2 plus 4, oh sorry, plus 5 into x3 plus 3 into x4 plus 1.5 into x5. This is PC1. And similarly, you will have PC2. That when you take, you will get this. Okay. So for those who want to see more about how this PC1, PC2 will be actually derived from these kind of a linear combination, we will look at a Python code, guys. Okay. We will look at a sample Python code to understand. Mm, yeah, to understand PCA model a little bit better. Let's see that.
Sir, but before applying PCA, so we have
Yeah.
to do scaling, right?
Yeah, we have to do scaling. Doing scaling is useful. Yes. Just give me 1 minute, guys.
What type of scaling are you going to use?
Scaling is it is to transform your data range into a smaller range for all of the features. You might have x1, x2, x3 until x10. So x1 can be salary, let us say, which is in lakhs or in crores. X2 is experience, which is usually in 20 to 50, or 10 to 50, or 2 to 50, right? So sometimes the salary numbers will be dominating the experience, smaller numbers. We don't want that to happen, because experience is an important feature to be able to consider to capture the relationship, right? So we will convert everything, all of the feature, into certain numbers, let's say -3 to +3, okay, or -1 to +1, or 0 to 1. We can do anything. This is called normalization. This is called standardization. So there are
-3
many
to
techniques. We
+3
can
is
do
valid.
anything. This is mostly used. Okay. Yeah. Okay. So have a look at this small case study, guys. This is just to explain PCA. If you see, there are around 15 or 14 features, sorry, 18 features over here. So definitely for 18 features, PCA is not required, because there are many models like decision tree, random forest, XGBoost, AdaBoost, gradient boosting machine. They will easily work on 18 features, 30 features, 40 features also. There is no problem, right? Like I said, PCA was invented at the time when these models were not there. Deep learning models were not particularly used in the industry because of the computation power not available. Fine, we'll just see this to understand PCA. Fine. So I have a data set which consists of this. We can directly look at the data. So this is university admission data, right? You have different universities like um, Alaska Pacific University, Abilene University, different universities are there. All are US universities. And you can see some information. Applications received, accepted, enrolled, top 10%, 25%, full-time undergrad, part-time undergrad, outstate, room, books, personal expenses, PhD expenses. I think this is payment. We will see. Terminal, student faculty ratio, percent alumni, expenditure, graduation rate. So, okay, and all these data belongs to 12th standard people, 12th class people, because after 12th class, they will apply to the undergrad. Okay, so we have this information, guys. Let's look at number of data points, 777. Total 777 universities are there, because for every university, you have only one record, which represents total number of applications received that year. Out of the applications received, how many did the university accept? Out of the accepted, how many did the university enroll? How many the students finally enroll, and so on. Okay, and you can see the details about this particular fields here. Name refers to name of university college. Applications received. Let me close this. Yeah, number of applications accepted, number of students enrolled, percentage of students from top 10% of higher secondary class. Out of top 10%, okay, out of all the students, how many students are having top 10 percentage score in the higher secondary class? Similarly, this one represents top 25% score. Number of full-time undergraduate students, number of part-time undergraduate students, outstate. If somebody is from out of state, cost. This is also cost. This is also personal expenditure cost estimation. So you have all of these. A percentage of alumni who donate. So you have information about students and universities. Now on this you will apply PCA. Initially there are 18 features. You look at data.info, you can see some information. There are no null values, so you don't have to do any pre-processing to deal with null values. There are 777 unique universities. And I have removed the university name. I removed the university name because university name is not important to actually predict anything. Okay. Now, when you do describe dot transfer, transpose, T transfer transpose, you can see the descriptive statistics, guys. Okay, number of applications, mean is this much. Applications mean is this much, standard deviation, minimum, maximum. So you can see all of this. Okay, that's not the main point for us. And there are some errors. So I will just remove the records or change the records which are having the error. So there is a record where the PhD is greater than 100. Once again, I will show greater than 100, which is not possible because the PhD column stands for percentage of faculties with a PhD. It cannot be greater than 100. Maximum is 100%, right? So I'll just changing that. There is some error, so I'll just change those in the few records. And then some graphs to analyze the data. Okay, but we will go to, yeah. Now, one important thing here, you see this. Yeah, so you have these features. Can you tell me, will there be any correlation between these features, guys?
Yeah, definitely.
Okay, okay, good. What could be the features which are highly correlated?
Top 10%, top 25%.
Top 10% and 25%. Yes, very good. Definitely. Yes, that will be correlated for sure because top 10%, once again, is within top 25%, right? Similarly, applications received, out of that, how many the university accepted, out of that, how many the students joined will also be correlated, right? Because
Yeah,
this is a subset of this, and this enrollment is a subset of accept and as a subset of application. So that will also be correlated. So like this few,
outstate room boarding because people is
correct.
Yeah.
Correct, correct. Yeah, outside room board because people who are coming from outer state will go for room board. That could also be there, yes.
And
So
only
we'll
PG
just
people can take PhD, right?
PG people can take PhD. Yeah, exactly. They can take. So you can see some this thing over here, correlation you see. Number of applications versus how many university accepted at the bottom you can see here. 0.94 is correlation. And number of applications and enrolled 0.85. Number of accepted applications, one second, number of accepted applications versus number of enrolled finally, 0.91, very big correlation. Also top 10% and 25%, let's see. Top 10% and 25%, 0.89, this is also very high. Let's see, PhD, with PhD, is there anything? 0.85, PhD and terminal. Terminal stands for, it stands for terminal. One second, guys. Let's see what it is. Yeah, percent terminal is exactly, I don't recall. Let's see what it is. Percentage of faculty is a terminal degree. I think it's postgraduate degree. It's something mandatory degree. So obviously it is not mandatory, but added advantage. So yeah, there will be correlation, obviously. So there are a lot of correlations. So it's not good to have all of the features, right? But it's okay with respect to some models like naive Bayes and other ones, but otherwise it's not very good. So what we can do is first we will, yeah, again, if you can see this, guys, for all of the positive correlated, these are there. Negative correlated, these are there. Negative correlation is also there in the data. You can see that, right? So now we will apply PCA model. Very, very simple process. Just 5 to 6 lines of code. That's it. Okay, first we will do scaling. Standard scalar, I created an object and scalar dot fit transform on my data set. right? And columns, I need to tell which are the columns. I have to tell what the column names are. So I'll tell the column names. So after this is applied, I will have this as my new data. Everything is between -3 to +3, as you can see, right? Everything is between depends on what level it has scaled. Sometimes it can be from -2 to +3 also. It depends. So now totally I have scaled the data on all of the records and I have 17 columns. Okay. We will apply PCA model. The process is very simple. As you can see here, I have this PCA class and I'm creating an object. I'm telling PCA class number of components are 17, which I can save it in a variable called n data dot scaled, the transform data. In that shape, I will get the shape, and out of the shape, I will get number of records and number of columns, right? When I do shape, I only want columns. That is why I'm selecting square bracket 1. This will give me only the columns information, which are 17 columns. So number of components initially are 17. Okay. And random state is just to begin with what kind of columns or what data. So it's, you can just take any random state so that you end up getting the same particular principal components, right? So this is how I created the object. Okay. And then finally I have to do fit underscore transform. PCA. I created PCA with 17 components and I'm doing fit dot transform on my scaled data. And I'm converting everything into data frame because I will get in the form of vectors, like I told you, which will be maybe array representation or list representation in Python, right? But it's actually a vector. But when we combine all the vector together, we put it in a data frame. So I'll rename the data type into data frame like this. And I'm saving it into new data frame called data underscore PCA. Okay, great. Now, can anyone tell me how many principal components will be created?
17.
17, exactly. If there are n dimensions in the original data, n eigenvectors will be there. There is a property. Okay, n eigenvectors will be there. If there are n eigenvectors, then there will be n principal components, right? So let us see first. And also one more thing, guys. Principal component 1, principal component 2, 3, 4 until 17 will be there. And the first principal component will capture majority of the variance of the data set. And second principal component will capture second best majority of the variance. And third and fourth and fifth and so on, right? So if you can see, I have taken the PCA model, which I have built, PCA model, and I am asking explained variance ratio. Explain variance ratio. See, I can show you explained variance and explained variance ratio. I think, okay, I'll come to that. So what this will tell is explained variance by each of the principal component in terms of percentages or ratio of the overall. So the first principal component covers 32%, but I will not take only one principal component because that will give me only 32% variance coverage of the original data. Right, I want at least 80% of the variance to be covered. Right, so I will take second also. Combined together, how much it is covering? Around 40, 60, 58% of variance is covering. Still not satisfied. Right, so what you can do is you can build a graph like this, cumulative graph. Right, if I take only one principal component, that is initially I have 17 features like this, right? And the data is somehow spread in n dimension vastly like this. I will take this. This is one principal component. This is another principal component. Okay, one second. This is another principal component. Fine. Just for example, let us say, if I take only this, okay, then it covers 38% of the variance of my data set, right? So initially 17 dimensions I had, these 17 dimensions covered how much percentage of the variance of the data?
17 dimensions cover 100.
Yeah, obviously all my
100%.
data is in the 17 dimensions, so it covered 100% variance of my original data. Now with the new dimension, it's covering only 38%, so it's a loss. I don't want it. So I will take this also. And I will take PC3 also. PC3 may be something like this, right? And PC4 may be something like this. Like this, again, I will have 17 dimensions, okay? But again, if I take all 17 dimensions, definitely it will cover 100% of the variance, for sure. But what's the point of taking 17 again? Already I had 17 initially. After doing PCA transformation of two new dimensions, again, if I take 17, what's the use? No use. So it makes sense if I take 3 dimensions or 8 dimensions or 10 dimensions, still it is better. Still it is better, right? But if I take only 1 dimension, it is covering 38%, let's say. If I take 2 dimensions together, 1 second. If I take 2 dimensions, this one and this one together as the new dimension, it is covering 58%, let's say. Still not good enough. If I take 5 dimensions together, let's see here. 1 dimension, if I take 32%, 2 dimension, 58%. 4 dimensions together, if I take around 71%. This seems good, 86 or something like that, which is equivalent to 7 components, 7 principal components if I take. Or this is also good, 8 principal components. 8 principal components if I take, it is covering 90%. So look at this. 17 old dimensions, old original dimensions are explaining 100% of the variance of the data. Okay. And 8 new dimensions are explaining 90% of variance of data. So obviously it is better to deal with 8 new dimensions, right? The loss is less, right? Still, there will not be major changes in terms of predictions. It will be okay. But this one will give problems for sure, because there is already correlation among many features, as you have seen, right? And also, some are unimportant. Some are unimportant. When you look at the correlation between target variable and input features, you will see that. So considering all these, there is a high chance of overfit, right? Or sometimes if it can be underfit also sometimes if the variance is not captured properly in another data set situation, right? Not in this in this data set, there is a chance for overfit only, right? But if you deal with this, right, where each principal component is linear combination of original features itself, but these are new dimensions where correlation also is not there. Therefore, it will be better to work on this. Also, models can easily be built on lesser number of dimensions than more dimensions, as we have seen this. But this is only true in the past. Right now, any model will easily work on even 100 features or 200 features. No need to worry. Okay, but we need to know the concept, right? Why PCA was built. That is why we are learning this. Okay. Yeah. So now let's see. Yeah. Now let us see the main part, guys. So assume I will take four this thing, 4 principal components covering 4 principal components covering 72% of variance. Yeah. So I have given a code to check how many principal components are required to get at least 70% variance. So it turns out it is 4 in this case, as you can see in the graph also. Right. So my new dimensions will be these, right? PC1, PC2, PC3, PC4. Okay. And I'm showing you the eigenvector of each of these 4 principal components. So you know that 17 eigenvectors we will get. Sorry. Seventeen eigenvectors we will get. Okay. And I'll take 1 second. V1, V2, V3, V4. We will only deal with the first 4 eigenvectors because I have decided to take only 4 new dimensions. Okay, the first eigenvector is this, guys. It is this, right? Observe this properly. The first eigenvector is this one. This is the eigenvector. Okay, or I will put it in the vector form like this, which I am able to display. The eigenvector which I got from the PCA model, I'm just displaying it over here, right? It's simply how to do is principal PCA.components. Your components you can ask to show from beginning to 4, right? I'm asking it to show. Okay, first principal component is this. Second principal component, oh sorry, first eigenvector. Second eigenvector is this. Second eigenvector is this, right? And if you observe, I have displayed this beside the original dimensions. What's the reason for this is because PC1, principal component 1, is not exactly equal to eigenvector, right? I told you it is linear combination of original dimensions, right? Principal component 1 is equal to this, It is not equal to eigenvector. Okay. Principal component is equal to linear combination of original dimensions, but we need to know what the combination is, right? So for example, when we built a linear regression model, we know W0, W1 x1 plus W2 x2. We know that output is a linear combination of inputs, right? But what is that combination? What is W0? What is W1? What is W2? We need to know that. For example, 3 plus 2x1 plus 7x2. Okay. And we found this using gradient descent algorithm, optimization algorithm, right? We have also seen the gradient descent code, right? Guys, did we see gradient descent code? I don't remember. I think we saw.
Yeah, we saw.
We saw that. Okay. Yeah. So we know what the this one combination parameters or weights are. Similarly, here principal component 1 is, I will just write it like this, W0 x1, okay, W1 x1 plus W2 x2 plus W3 x3 plus W4 x4 until W17 x17. Principal component is linear combination of original features, original dimensions. But what is that combination? It is linear. Great. So I just put x1, x2, x2, power 1, power 1, power 1, power 1, power 1, power 1, everywhere power 1. It's linear, so I can write it. But what is W0, W1, W2, W3, or W1, W2, W3, W17 is what we will get from this eigenvector. So this is the eigenvector. Okay, this is the eigenvector. So it is equal to 0.25 x1 plus 0.21 x2 plus 0.18 x3 and so on until the last one is 0.25, as you can see, 0.25 x17. This is equal to principal component 1, original combination, linear combination of original features. Okay. Similarly, you can see principal component 2, 3 and 4. Just exactly what I have printed over here also. Principal component 1, observe this principal component 1, this one, straight away. Okay. But again, let us see one more last additional step, which majority of people do not know and understand. Everybody can tell till here. Mostly I've seen in interviews also, I've observed this. But they do not know how the data is getting generated or transformed, which is still funny. I don't know why. So let's see this. Here, how did we get this data? How did we get this data? PC1, PC2. This data, how did we get? Is this the original data itself, guys? Can anyone tell?
No, it's not. No, it's not the
Yeah.
original data. It's the covariance. Variance. What is explained? I mean, like the transform the PC1
Yes.
and
It is transformed. How did we get these points? See, I will draw this 17 principal components. I had this data. Is this data same as this data?
no, it's not.
No.
Correct. And how is this data point generated then? You know how PC1 is generated, PC2, you know this, how this is generated. It's the same way. Okay, let's see. Now we have this, for example. X1, X2 until X17. 3 to 10, some values are there. First record. Let's say first record belongs to this one. Sorry guys, this one. Okay, this one should be taken, each point will be taken and it should be converted into, here I am taking only P2, PC1, PC2, Y. Okay, here also you'll have Y. Let's say Y, let's not deal with Y for now. Sorry, Y won't be there. Y is not transformed, only input is transformed. Okay, so we need to have this. But I know what is PC1, right? It is 0.25 into X1 plus 0.3 into X2 plus 0.2 into X17. This is exactly how we will get this point also. So this is a substitute, this, you substitute 3 here. You substitute 2 here. And this is 10, let's say. You substitute 10 here. What will you get? You will get one number or 2 numbers
Only
out
one
of this.
number. Only one number.
Yeah, let's say it is 3 point, let's say it is 0.7, for example, 0.7. So for the first record, it is 0.7,
Okay. Mm.
right? So that could belong to this one, let's say, for example, which means, just for example, I'm telling, which means this point, which was this, in these 17 dimensions representing this row, now its equivalent is this in 2 dimensions. This is 0.7, let's say this is 0.7. And similarly, point PC2 also you can calculate, right? Using the same, whatever PC2 will be, that linear combination of original features, you will calculate, and let's say it is 0.9. Okay, so I'll put here 0.9. Right? So this point in original 17 dimensions representing this record was this. Now that is equivalent to this point in 2 dimensions representing this record. It's record in the transformed space. Okay. So like this, every record will be calculated. The principal component values will be calculated. Right. And if you are having a Y, then Y will be as it is. Y is not transformed, right? Y is not transformed. Y will be as it is. Only inputs dimensions are transformed. So this is how you will get it. And I have actually taken some output to show to you. This is how you will get it. Okay. So please, if you face any interview, still people ask PCA to check the basics actually. So please explain this point also. Take an extra time to explain this point, how the data is getting transferred using the equation, linear combination equation you're getting. Anyone will be really just impressed with your knowledge. Okay, so now this is what principal component is. After this is done, now we have to look at auto encoders, because it will take only 15 minutes or so. But before that, any questions, any doubts?
There is a function explain variance. What is that full ratio? Explain variance ratio. Can you scroll down?
Yeah. Yeah, this tells how much variance is covered by each principal component.
So is it where it is from defined, the particular thing? It's already there.
Yeah, this method is a pre-built within the library.
Okay.
You just have to call it.
Okay, thank you.
Yeah. So all otherwise, I'll also show you. Again, if I can read this. Yeah, so if you do PCA dot explained, then you can see two things. Explained underscore variance will show each principal component is covering how much variance at a numerical value. But see, the total variance you can always get by adding everything, all the 17 principal components, right? You can get it. What is 5.45 out of the total? So you can always do this of 0 divided by this dot sum, right? I think I have sum of this 32%, right? That is what the first principal complex. Otherwise, you just use this dot ratio. It will give you the ratio by default for every principal component. And so usually we'll use this only because the number itself is irrelevant. How much percentage each PC is covering is what is more important for us. Okay, great. Now, finally, let us see about the last topic in neural network, deep learning, guys, which is autoencoder.
Manikant,
Yeah,
I
yes,
have one small doubt.
yes,
It's not related to PCA in general, I'm asking.
yeah, yeah,
The correlation value lies between -1 and 1, right?
yeah,
But in
-1
heat
and
map, we always get the values between 0 and 1. 0 means there is no correlation and 1 means strong positive correlation, right? So why aren't we considering the negative correlation? I earlier also I had this doubt.
no, can you repeat that again one more time?
The correlation value always lies between -1 and 1, right? -1
Yes.
means strong negative correlation and +1 means strong positive correlation and 0 means
Yes.
which has
Ah.
no correlation at all.
Ah.
While we check for the correlation using the heat map, we will always get the values between 0 and 1,
Ah.
right?
We have negative also. You see here -0.18 and -0.01, -0.29. There is a strong negative correlation also. I will show you one second. It is between SF ratio and top 10%. Let's see that. Top 10% and SF ratio. Yeah, -0.38, which is like a medium, below medium negative correlation. As you can see this, right? So negative, positive, both should be seen. The type, yeah, both should be seen. Positive correlation, negative correlation, any type of correlation you have will impact the model finally. Okay, so you should try to avoid both in the data set.
Yeah, I got it.
Yeah, I think probably in the example so far, what you guys have seen, maybe
The values are
always,
between 0 and 1. That's why,
yeah, yeah,
this is the first time I'm seeing the values in the negative. Okay, thanks.
negative. Yeah, but both in the real world, definitely both will be there. You should observe both for sure. And there is no doubt
Yeah.
about it. Okay, right. Okay, let's continue, guys. So this is about autoencoders. Okay, 1 minute. Very, actually a very beautiful and, to be honest, a simple approach also, guys. This autoencoder is actually very beautiful, elegant, and a simple approach to be able to get what we want. It is very intuitive. First, I will write it. It is very intuitive. Means easy to understand, actually. Easy to understand. Anybody who has the data scientist thought process, right? How a data scientist should be actually thinking, that kind of mindset, will easily grasp this, right? And that is why I want you to think in that direction also. And I will tell you how to think to be able to understand this properly, right? And second important point is, this is sort of like the beginning of many advanced unsupervised deep learning models. Advanced. This is also obviously a deep learning model only, right? But there are many advanced guys, right? So you guys might have heard about these terms, BERT, okay, encoder decoder architecture, if you read the if you read blogs regularly, you might have actually heard about these terms, right? That these are all advanced from this this one. So everything will keep getting evolved, right, from one model to other model, and that's what happened. So if you look at this term auto encoder, encoder. So what is the meaning of encode in
Converting
general?
something into a code. Right.
Yes, exactly. It is to convert um to alternative, usually why we convert to new space or numbers, right? We all have heard these terms decode, right? When will we decode anything? When something is encoded, right? When something is uh, password protected or encrypted, that is when we have to decode, right? That is when we have to decode anything, right? So the major idea is that we have a certain data, right? If we can encode it, encode it into smaller dimension, smaller dimensions, okay, sorry, uh, encode it into smaller dimensions, and we also know how to decode it, how to decode it, where we end up getting this original data back again, almost I would say, because not always you would get the original data. So this one would be in smaller dimensions, duplicate. Yeah, sorry. Hmm. Okay, this is the idea. Okay, now we will look at the architecture of autoencoder. I will just put the image also because I will share these notes. Yeah, this is best. So these are some examples, guys. And mainly we have to figure out how and why it is working. Okay. Like I said, it is actually easy to understand. First, we will see this one. So every this thing you see is like a layer. It's like a this is the input layer. This is the hidden layer, hidden layer, hidden layer, hidden layer, hidden layer, and output layer again. Okay. One important thing to understand is the number of dimensions in input layer and output layer will be same. Number of dimensions, obviously it means number of neurons. Okay. Okay. So initially I have an image, let us say I have an image which is represented using 1080 pixels. So just assume there are 1080 images, 1080 neurons, right? And for every this thing, you have a representation. So here I'll just put the data, guys. Just 1 second. Okay, it's not working. Like this, I have 1080 pixels, for example, and this is 30, 20, 20, 25. This is this particular image, right? One image is represented as a row in my data set. Like this, I may have many images, right? Many images I may have. Okay. So every image I can take and let it pass through this architecture. Let it pass through this architecture. What is happening is observe the intuition behind this. Initially, I have 1080 neurons, right? 30, 20. That is what will be the values that will go. 30, 20, 25, the values will go here, okay? And it will go through this particular uh, forward propagation that you know. And here I have lesser number of neurons. Always it will be in the same structure only. The number of neurons here will always be less than the previous layer neurons, right? In the encoder phase. Encoder phase. There are two phases in autoencoder. One is encoder phase, other one is decoder phase. We will understand why it is called like that. What is happening over here is initially something is represented in 1080 dimensions. Later that got uh, uh, transformed or converted into a smaller dimension, let us say 500 dimensions. That again later got represented into 200 dimensions. That again later got represented in 50 dimensions, let us say 50 dimensions. So successfully, the representation of an image in 1080 pixels somehow got transformed into 50 pixels, 50 features, you can say 50 features. But it was not done straight away. From 1080 straight away, I did not reduce it to 50 features. From 1080 features, I reduced it to 800. From 800 to 300, 300 to 50. Slowly, one by one. Because if I directly do this, then there will be a lot of loss. Okay, so slowly, one by one, the transformation has happened. Okay, which means it is like I have transformed it, I have converted it. So here what would happen is uh, the most important aspects would be captured. So you can see a lot of times an image like this, which is blurred, but it is able, you can see the features little bit clearly, hand, face, hair, you can see the features, but it is overall, it is blurred, right? It is represented as a uh, compressed image, compressed image, right? Because the number of pixels it is used to represent is less, so the clarity is obviously not there. The main important features are available, but the details and the enhancement and the distinction is not there. Okay. And you guys, I think all of you guys know this, you know, when we watch movies, we prefer for 4K. 2K is also there, 1080 pixel. Why do we try to prefer for this? Because we know that the greater number of pixels, the greater the clarity, right? Or the greater the details, right? That is why we prefer that. That's exactly what is happening here also, guys. The greater you have, in particular to images, the greater clarity and details you can see. Otherwise, only the major features, the representing the image will be available in the smaller dimensions, which is exactly what is identified in this process. Okay. Until here, it is encoded to smaller one. And then later, this 50 values in the 50 dimensions is taken, and that will be a little bit decompressed or expanded to, let's say, 300 dimensions, from 300 to 800, and 800 to again 1080 pixels. Again, here if there is 1080, again here also you'll have 1080 only. So it is like taking an data, transforming it into lower dimension, and then getting it back to the original dimension successfully with minimal loss. Minimal loss. Minimal loss, because there is no guarantee exact same thing you will get it, right? Because after all, this is a model, and model is never 100% accurate. We know that, because if you deal with only one image, you will always be 100% accurate. But you will deal with millions of images. For all the millions of images, the training would happen, and you will get the weights. You would get the weights values. The weights values that we get is actually learnt across millions of images. If it's only on one image, the weights will be exactly fit. It will be overfit. You will always get the pitch perfect image. After compressing also, when you decompress, you will get the same thing. But you know that the model will learn on many images, and the weights will be learned in such a way that the loss what you take here out of the output, this thing will be minimized. Okay, will be minimized. So this is the entire idea. As you can see, just look at this particular simple example. Look at this simple architecture. This is one side, this is another side. Encoder, decoder. One side is to transform the data to lower dimension. Other side is to bring it to the original dimension again. So you are reducing it into smaller number of neurons, and here you are increasing it to bigger number of neurons. That is why the architecture is like this, and it's called auto encoder, because we are not creating any encoder logic here. What is the logic between input and the encoded value? We don't know. That's why we are building a model which will learn the weights with respect to the data and the loss function and so on, right? So it's called auto encoder. It is called encoder because first we are encoding it, and then since we know, we will decode it. A decoder also, see, it is like you see this the same image, you are getting it back again. Same image, you are getting it back again. In the middle, you are just compressing it.
Sir, is it like the image which you are giving input, right?
Mhm.
So, till the, till the compression part. So, is
Mhm.
it like PCA, like the dimension will be reduced,
Yeah,
right?
yeah, exactly, exactly. It is like PCA, which is reducing the dimension. That is exactly why I explained PCA before I was before I explained this concept, autoencoder. It is important, and I will compare PCA versus autoencoder also now. But first, let us clearly understand this. But you're right, it is like PCA. It is,
And
yeah, yeah.
yes, sir. And for loss, we use certain functions, like light is
Hmm.
for like mean square or something like that to optimize it.
Yes, yes, yes. We will do that. We will
Okay.
use different loss functions, right? And it depends actually when we deal with images, there are particular loss functions for text, particular loss functions, but mostly it is more or less same. But there are predefined loss functions, so you don't have to worry about it.
Yes, sir. Got it.
Okay. Yeah. So you can see it, right? How it is reduced and how it is again. We get it back to the original dimension. So this is you see the diagram, you're able to grasp it. You're able to grasp it. How that is why it's called very intuitive. This part is called encoder. This part is called decoder, right? And it is very, very important, guys. Extremely important, because like I've told you, this variety, variations of autoencoder are there, and they are used again. People have built on top of this and built complex architectures like BERT, encoder decoder architecture, right? GPT. All these are based on these deep learning models, particularly unsupervised like this one. Okay, so is this supervised or unsupervised?
Unsupervised.
Unsupervised.
Okay, what is it?
Unsupervised.
Unsupervised.
Yes, it is unsupervised. Because what we are aiming for is this decoder part, encoder part, which is obviously we don't know what it is. Not like we're giving input output examples, right? We have input and we are transforming it to this way. It's similar to that. Okay, fine. Right. Now, just a small, very, very important, extremely important point to compare PCA versus autoencoder. Right. So, on a very, very basic level, this is the first distinguish, that is the nature or intuition or approach of the model we need to understand. Is PCA a linear model or a non-linear model?
Linear model.
Linear.
It is a linear model because we know that principal components are that we are finding. Principal components are nothing but new dimension, which are
Linear combination of Fourier features.
yes. Okay, so what can you tell about autoencoder?
It is
It's
also
both linear and
yeah.
non-linear.
It is both linear and non-linear. So one answer is it is both linear and it is non-linear. Any other answer?
Non-linear.
Okay, one answer is non-linear. Okay.
I think linear.
Any other answer? So see, if you guys are stuck sometimes like this, and this can happen in interview. See, obviously you cannot cover every point in deep learning or machine learning, right? You cannot like cover everything. You have to derive many things based on your knowledge. Okay, so even if you read 2, 3 books also, still there will be some points which are not covered in the books. It will always be there. So you have, based on your understanding and knowledge, you can derive many things. So you see this neural network architecture and you think, okay, this is how the neural network architecture is. And what I'm getting is this. This is the new dimension, let's say, which is having 30 dimensions here, for example. Original dimensions are 1000, for example. Now you think there is the relation linear or non-linear?
Linear.
Linear only. Okay.
Linear.
Linear. Okay. Okay. Anything else? Linear, then why linear? Non-linear, then why non-linear?
Okay. So, why I'm telling linear is like we are taking all the input features and we
Yes.
are reducing it, right? So,
Yes.
it's nothing but the combinations, right? We are taking, yeah, the linear combination, as you said earlier.
Uh, it may not be necessarily, but okay, let us say that is also a possibility. So we will keep that. Yes, we will
Maybe
take.
we are going on gradually decreasing or increasing
Hmm. Hmm. Yes, we are
the
decreasing it. We are decreasing the number of features. That's absolutely correct.
yeah.
Okay, now
Maybe
think.
possible due to linear combination.
Mm-hmm. Mm-hmm. Okay, so what all deep learning models we studied? We studied a multi-layer perceptron, that is a basic ANN, a CNN, RNN, LSTM, autoencoder. This is now we are seeing. Uh, RNN, LSTM, is it linear or non-linear model?
Non-linear.
Why is it non-linear?
Yeah, because we have the activation functions and it is a complex model and we have the
Correct.
non-linearity.
If there is no activation function, it is almost equal. It is equivalent to
Well,
linear,
yeah,
right?
exactly.
Just a
Hmm.
function within a function within a function type of thing, still linear.
Hmm.
So isn't it the same here also? Can't I have activation function here tan h? Tan h.
Yeah, we have the activation function. Definitely, it's a nonlinear model only.
Exactly. So this one is derived. This one is definitely from this one. And if I have weights here over here, the relationship is linear, definitely. But if I have a activation function here, tan h, or I have here tan h, or ReLU, leaky ReLU, right? In that case, what is happening? This entire relationship is non-linear, obviously. Non-linear,
Yeah,
obviously.
exactly.
Yes. So autoencoder is typically non-linear, guys, because we will definitely utilize and take activation functions. Okay. When we have the opportunity, we will take activation functions because a relationship expressed in non-linear way is much better. It will capture more uh, variety and details when something is in non-linear way than in linear. Of course, it depends upon the data, but usually when we deal with images or text, obviously it will be complicated. The data itself will be non-linear in pattern. So obviously, when you transform the data into lower dimension, you have to have that non-linearity to be captured. So you'll go for non-linear approach. Right? So for complicated data, PCA is not that great enough. Autoencoder is definitely great, right? But like I said, many models can deal with higher number of dimensions. It's not a problem. It's not a problem. But still, people use autoencoder for variety of cases like this. Variety of cases like image compression. Okay, and one small example is see language to language translation, guys. Okay, I'm just giving intuition. Here, some sentence in English that is converted into numerical representation, you have this. English decoded and then encoded into German or Tamil or Telugu or Hindi, whatever it is. That I can use it here, right? Yes or no? Word by word, I can do it. So still these kinds of models are used, autoencoder dimensionality. It is dimensionality reduction only, but used in many ways. It's not used to reduce dimension. It is used to capture the most important features, which are called as latent features here. You can call it as latent features, which means important aspects, which is derived from the model. Latent means features that are not directly present in the input data, but have been derived with a combination of all these linear combination or non-linear combination, whatever, derived, and we have the extreme important information about the data set. Right? These are called latent space. When we have the latent space, we can actually take it and then decode it back to the original image, or we can actually generate more things. Somebody will say take Mona Lisa picture and add a hat to it. So Mona Lisa picture latent representation will be saved somewhere, not the entire representation. That way the memory also will be saved. Memory also less is utilized. The latent representation is taken and it is encoded along with another layer called hat. First, it will be encoded, and then on top of it, one more layer called hat will be again added. So you will get a hat on top of Mona Lisa. And so multiple use cases like this are there, right? One more is how are you doing? So how are you doing? You know, latent representation is used, but that is again converted into German, let's say. So like this, multiple examples are there. Okay, you can think about all the situations where you can use mm, to capture the latent information and from that derive something else or add something else or modify something else. Okay, all the graphics, editing, most of the things are done using encoder decoder approach. This is the beginning of it. Okay, it's the most simple. This is the most simple one. And I will write here, this is non-linear combination, non-linear model. Okay, when you have activation functions. If you don't have activation functions, yes, I will agree, it is linear only. Okay, but mostly you'll have this. So you can tell, if somebody asks in interview, you can tell that, there are multiple dimensionality reduction approaches. PCA, using PCA, it is simple, and we can get it's a linear model, and using autoencoder, it is also simple, but very efficient. Using the activation functions, we can get the non-linear representation of um, new dimensions with respect to old dimensions, and you will get the latent features representation also. Here you cannot see any latent features representation. The only principal components you can see directly, new dimensions. New dimensions you can see. Here also you are seeing new dimensions, but it is acting like a latent representation. That is something that has been discovered. Right? Here it is not like that. Nothing like that. Here I have latent. Features. Okay, yeah. So always try to do this, guys. Take two models and keep comparing one by one. For example, as a homework, you can take decision tree and maybe logistic regression or linear regression and compare these both. Okay, decision tree, is it a linear or non-linear model?
Decision tree is definitely a linear model.
Non-linear.
Mm-hmm.
Um,
Why? Why? This
It's
is
a
age.
non-parametric model.
It is non-parametric model. Okay. Okay. Salary. Okay. You see, you have the data which will split based on age, let us say, greater than 32. So here I have 30. So will I have one stump on the data like this? Okay, I will put the data, guys. Is it correct?
No.
Why?
It is correct on the
Age greater. I have the entire data initially, which is this entire data. Now I am splitting it into two parts based on this condition. So it got split into two parts. Greater than 30 is this, less than 30 is this. It's correct. Okay. And now let's say this one again will be split based on salary greater than 10 lakhs. Fine. So this is some, okay, I'll take this as salary. This one I'll take again, this will be Y. Salary, let's say 10 lakhs is somewhere like this. And observe, this is this data. So, age greater than 30, which is this. Age greater than 30 is further split into two parts. The data present in age greater than 30, which is this, is further split in two parts whenever salary is greater than 10 lakhs. So it will be something like this. Right? So here I'll put this just for this one. So you see how the accuracy improved. Here many are class 1, one is class 0. Here many are class 0, one is class 1. So initially until this level, let us say accuracy was 80%. Here it is 95%, 95% accuracy. So accuracy improved. That is why the split happened. Right? But you can calculate it using Gini index and entropy reduction. I agree. But example I'm telling. So now what is the decision tree model? This is the decision tree model on my data set. This is the decision tree model. So can you tell me now, is it linear or non-linear?
Linear model.
Non-linear.
How is it a linear? This is the model, right? This is the model. So see, if you only one straight line is linear, two straight line together, it's this which is non-linear. One straight line is linear, right? This is not linear anymore. This is non-linear. It is not a one straight line, right? One straight. It is like this. It is non-linear. Anything other than straight line is non-linear. Anything other than this is not a straight line. This diagram is not a straight line, right? It is T. It is like T structure. I mean, for example, I'm telling This is also nonlinear. This is also nonlinear. This is also because why? Because it's not a straight line. Simple. This is only this is linear. Anything other than that is nonlinear. Now I can have further more splits. Okay, like this one. And then this one. And then this one. And then this one. See how complex the model became? This entire part is the model. Right? If I split again and again, obviously you will have more stumps added, right? Like this. That's exactly what I'm doing. Okay. So obviously it is non-linear. First distinction between Bayesian tree and logistic regression. And then you can add more. Add more. You can think and you can add more. What is the time I need to explain about few other topics? It's already 10, guys. Okay. So this is all machine learning. So let me not get into detail of this. Yeah. So we have completed all of the topics. Let me come to. I want to quickly, please stay for 10 more minutes, guys. I want to quickly recap the most important points we have studied. Okay, please stay for 10 minutes. Yeah, so important points that we have learned. One by one, let us write everything. So it should be like thought we are thinking together, okay? So artificial neural network is, first of all, it is inspired by human brain. Yeah. Please remember some facts about human brain. I know it is very good to, learn about these things also. Very, very important because obviously from human brain only everything is getting inspired, copied, replicated, whatever you call it, in all these models. So there are there are over 100 billion neurons and 100 trillion connections among these neurons. That's some important fact. ANN, it is linear without activation functions. I'll just write it one way like this. ANN is non-linear model because of activation functions. And don't take anything as granted, guys. When you have a activation function, it will automatically not make anything non-linear or linear. We have seen logistic regression, right? In logistic regression, we are using a logistic function, right? Which is a logistic activation function. We know it, we're using in logistic regression, but we learned logistic regression is linear model. Because when I say linear or non-linear, it is relationship between output and input features. Okay, I may use activation function, but I may have created architecture initially where relation between input and output is linear. I'll get the output and then transform that using sigmoid or tensor, whatever. That will not make the model non-linear. Okay, but ANN by default itself, the model is such a way that the relationship is non-linear. Okay, with activation function. So always know the basics properly. Okay, and what else we have learned is ANN is called a deep learning model when
More number of hidden layers.
yes, exactly how to take when hidden layers are greater than one, right? If you have two hidden layer also, it's called a deep learning model. 200 hidden layer also, it's called deep learning model. Okay, and then we have seen activation functions, guys. Can you quickly tell some activation functions? Sigmoid, yes,
ReLU,
Value, leaky
Licky
value,
ReLU.
yes,
softmax,
yes, yes, good. Yeah, optimization functions we have learned, right? Before that,
gradient descent,
yeah, you can tell that. Gradient descent,
stochastic gradient descent,
yes,
Mini batch.
mini
Red
batch,
Adam.
RMS prop.
Momentum
I
based.
like that also.
Yes, momentum based. I will write here. Okay, I'll just put it here. MOMEN, momentum based.
Add a grad.
Correct. Add a grad.
Adam.
RMS, what an Adam.
Okay. When will we use add a grad?
Sparsity. And the
Hmm.
swing is present.
Why should we use add a grad when there is sparsity in some features? And look at the word adaptive grad, adaptive gradient. You can remember from this.
For the sparse features, it will have different
Learning rates.
learning
Difficult
rate.
for all the things.
Yeah. Why do we need different learning rate for different features?
Because the
Especially.
weight change in weight will be very slow, so we will increase the learning rate for that.
Correct. And in terms of the optimization terminology, what is that situation called? Saddle region, right? Remember, when there is a sparsity in one of this particular thing, you will have like this, right? This region, you need to move fast, right? Here, you need to walk fast because there is no improvement. It's happening because of sparsity. And this region is called saddle region. We have also seen there are three major components we have to deal with whenever we encounter non-convex shape. Three major regions, saddle, okay, and two other, can you remember?
Local minima and global minima.
Yeah, that is one thing. Local, global, local, that is one thing. Okay, yeah, anyway, you can just quickly see the previous. See, I told you guys to make notes many times.
Yeah. It's when we are stuck at the
It
local
will
minima,
jump
when
out
the
of the
curvature
Mm.
varies in the
Right.
rotation of the rates.
Correct. Yes. And in all of these, we have some points called epochs, batch size, iterations. So what are all these?
epochs number of times it scans the entire data.
The
Yes,
whole data. Yeah.
Iterations number of times it updates
Weights.
the weights.
correct. Yes.
Batch size is nothing but the split of the whole
Yes.
data is getting split, right? Number of
Into
samples.
batches. And batch level, you will update weights. Right? Batch level, you will update weights. Okay. So this is again very simple question. By the way, you guys had exam, right?
Yeah.
In the deep learning also?
Yes.
Okay. So how did it go? Did any of these topics come up, and was it helpful?
Many was covered, but many were not covered also.
Many was
I mean,
covered.
like, yeah. Many questions we are able to answer,
Okay.
and some I'm not able to answer. Yeah.
Okay. No problem. Good. Yeah, always there will be many. We can always learn more and improve. Yeah, that will be there. Right. So, and cost function also, guys. Cost function, mean square error, and categorical cross entropy.
Binary cross entropy.
Yeah, binary cross entropy is one more when you have two classes.
Yeah.
More than two classes, binary cross entropy. Or simply you can say I will take softmax and add binary cross entropy as a loss function. That's it. Okay, this one. And there is also one more thing called ranking, guys. For ranking, you can actually, it's like used for recommendation engine, but that's is advanced concept. I'm just telling you, these are not the only two types of cost functions. That is one for regression, one for classification, but there is third type called ranking. Okay, we will see that later. I mean, in the advanced that will be covered, I think so. These are all basics. One more basic. Finally, tell me the metrics to measure the performance. You have accuracy, you have recall.
F1 score.
F1 score.
Yes, F1 score. You have RMSC, MAE. Okay, so many more are there. We have MAPE also, mean absolute percentage error, which is useful. Okay, so many are there. Right, so
R
next.
square adjusted R square, right? Manikant, RMSE.
No, that is for linear regression. R
Yeah,
square.
RMSE and MA.
Root mean square error.
Yeah. Like aspirants, just not square up.
No, they are not
No,
there
the
in deep learning.
Oh, it's okay.
Yeah, no, they are only for linear regression with respect to statistical approach. They are not there as a part of deep learning models. Okay, fine. Now, what else is important here? Cost function, this sum of neurons. Yeah, tell me all the hyperparameters.
Number of hidden
Number of
layers,
neurons. Number of
neurons in a hidden layer, activation
Hmm.
functions, optimization functions.
epochs batch size. Learning rate loss function.
Yes, yes. Optimization function, cost function, activation functions,
Weights and
and epochs, batch size. Yeah, these two will define it. Epochs, batch size. What else is there?
Learning rate.
What is it?
Learning rate.
Logging.
learning rate.
Learning rate. Yeah, yeah, yes. Yes. So these are some of the hyperparameters. Okay. Then what have we learned about CNN?
CNN is for images
Combination of
basically.
convolutions
Convolution.
is
It's a
ANN.
combination of both convolution operation and
Right. And why are we going for this is to cover the um, spatial coverage of data, which is needed for images. Because patterns would not be in a linear form, right? Pattern in an image will be in a non-linear form. So we need the spatial coverage of data, right? That is not linear. Why also just recap why ANN fails on images.
ANN
doesn't
tries to capture the linear, either horizontal
Yeah.
or vertical, and
Correct,
as
correct.
it also occupies memory, high memory.
It has many weights and
Exactly.
it tends to fit also.
Yes, yes. And high memory. Good point. Okay. And then in CNN, other important things are padding. We need to know why we are adding padding. And
Pooling,
yeah, pooling.
Right.
stride.
Yes, stride. This. And finally, here also we have all other things like activation functions. You have optimization functions. You have cost function, epoch. Everything is still the same. You know, just the approach is what is majorly different. Okay, 10th one, RNN. Okay, first important point is it is recurrent. That is feedback loop for the hidden layer. Therefore, it is a time series based model. Okay. Um,
Text data it is for.
yeah, on text data, it is good. And on any data where time series is there. Okay, stock price prediction, price of a t-shirt, whatever it is. Okay, and we have also seen how the connections are, right? It is important. Connections every time step. I'm not drawing the architecture here because already I've drawn it many times. So just imagine how it is, right? And also, downsides of this is it is good for short term. Short sentences, it is good. Long term memory, it will fail due to vanishing gradient and exploding gradient. Vanishing gradient and exploding gradient, due to these problems, it will fail, okay? And you can say it is good on few paragraphs maximum. It's not good on pages, or it's not good on books of data. Okay, that is why we went with LSTM. Okay, here you have two this one, two states. Memory, short term, long term. And you have gates included in the hidden layer, right?
Yeah.
Yeah. What are those gates? Input gate.
Circuit gate,
Sorry,
input
yeah,
gate, and output.
input and
Circuit gate, input gate, and output.
yes. This is straightforward. Over here, you will also have candidate. From candidate, you will filter and get the input. Okay. You will also have from filtering candidate candidates. I'll just put like this. Output gate also is straightforward, and then this will pass on to the next hidden layer in the same hidden layer. I mean, in the next time step. Okay. Because of this, it is good on any length of sentences. And GRU basic modification, where you have only two gates, reset gate and
Update
update
gate.
gate. Yeah. Okay. One more important point, guys. So far, whatever we have learned, RNN, LSTM, GRU, whatever you have learned, these are reading the data sequentially, one by one, time step by time step. Okay. But not reading entire data at once, which means if I say, hi, get me a black dash. So LSTM will read this first and then read this, make sense of it together, and then read this, make sense of it together, read this, make sense of it together, read this, make sense of everything, and predict that, okay, get me a black coffee is the prediction. 0.68 is the prediction. So it gave this. Fine, that is fine. But this is not the always the use case. There can be many times where it is clear that John worked hard and got job at dash since his joining He is always happy and love the culture at Microsoft here. What is this word?
Microsoft.
Yes, it is Microsoft. To predict this, obviously the model has to read words after the blank also. It's not like always you read initial words and predict the next word. That's not always possible. Sometimes you have to read words after the blank also to be able to make sense overall and predict it, right? But this model will, RNN, LSTM, GRE will not do it. It will only go one by one, one by one, one by one, and try to predict it. So here it will predict, it would predict, let us say TCS. TCS as the prediction. Why? Because most of the people work at TCS. Majority of the people. So as per the highest probability, TCS is what will come. So TCS it will predict. Second highest probability is Infosys. Third highest is, let's say, Microsoft. But that is gone. Only TCS will be considered. But when the model looks at these words also, it will predict properly. So these are not doing it as of now. But later when you when you'll come across generative AI, NLP and everything, you will also read about bidirectional RNN, bidirectional LSTM. Okay, which means what will happen is the model will also read. Okay, one second. Will also read the data from backwards also. Backwards also, like this. Like this, it will read everything. And this also bidirectional and able to predict this. Okay, like this. But again, this is also not good enough. So we have this attention mechanism. This is a very must and beautiful required use case mechanism. Okay, so here what will be taken is this entire sentence. It is clear.
Actually, we got one question
Yeah,
for
question from this
exam.
attention
This
mechanism.
attention mechanism.
Yes, I was about to say that.
Attention mechanism, you got a question. This is actually not part
Yeah.
of.
Many questions were from out of syllabus only, Manikant.
Yeah. This is a very this is generative AI. It is not part of like deep learning. You should tell that. I will
Yeah,
talk to them.
definitely based upon the scores, I'm going to tell Abhishek. Yeah.
Sure. It is clear, John worked. I'm telling this because in the future it will be helpful for you to connect the dots. Right, Microsoft have like this. So here a relation between every word will be captured. Every word. So even though here previous words I will see a relation between Microsoft and worked hard for Microsoft won't be captured, right? Because only this word, John, this relation with this will be captured in the step by step, step by time step learning. It is seeing one word by one word by one word by one word like this. Microsoft and culture will be captured relation. But Microsoft and he worked hard for Microsoft will not be captured by this bidirectional models. Relation won't be captured. So but the relation can be anywhere. The word beginning, for example, France, can be at the last, like I will visit again. Visit again. Visit refers to this beginning word called France, where in between there could be 500 words in between. So any step-by-step model which we'll see, it will lose that particular impact, capturing the relationship impact. So that's why there is attention mechanism. What it will do is it will take everything in left hand side and right hand side, and then it will try to find the relation between one word and all other words possible with itself, with this everything it will try to find. And like this here also it will try to find. If there are m words here, so m cross m relations will be captured, and each relation will have a score called attention score. Attention score. So for example, relation between clear, worked hard, hard work, and Microsoft score should be high, 150. Hard work and culture. Hard work, okay, culture will come later. Hard work and culture is less related. Microsoft and culture is more related. Here, Microsoft and culture, it is talking about Microsoft culture, so 250. Hard work and culture is not much related, so it will be 70, something like that. Okay, so that's how the attention score will be computed. So this is to let you know the limitations of these approach. Limitations of RNN, LSTM, GRU is that it looks time step by time step, word by word, like how we read. But sometimes it is not enough to answer things by reading previous words. It is we need a much more complicated understanding to capture. Okay, so
Sir, is
that's
it
what.
like here vector database will be used to compare the, I mean, like
No,
the
no,
numbers?
no, not required. Just a small. There is a formula for attention score. We have the key value and a quality score. Three vectors will be computed, and there is a formula with respect to all these three values. You'll get an attention score. Vector database will not come here. It will come in particular use cases like developing chatbot or let's say identifying the similar sentences and so on.
Okay, okay. But
Okay.
that is also very important, right? The
Yeah,
vector
yeah,
data.
definitely very important. All real world use cases in text data happens with the vector DBs only. It's also very important. Okay, so we have seen these. See, it's not the only things we have seen. We have seen many more things. For example, how to deal with overfitting issue. Very important, right? Dropout layer, dropout, L1, L2 regularization. Same like linear regression only. No, nothing new to learn. Okay, batch normalization, which is just to scale the data. These are some things to deal with overfitting issue. And obviously you can play with epoch. You can play with this hyperparameter, epoch, batches, number of neurons, number of layers. All these you can play with. Optimization function, cost function, whatever. You can just try with everything. Okay, and you can deal with overfitting issue. Okay, so I've just recapped all of the important points. There are many other important points, guys, obviously. So I request you to make more points in this and add this over here. So I will share this and PCA notes, autoencoder notes, and PCA code. I will share it right away. So you guys can access it. And you can, anytime you want, you have any doubt or anything, you can always approach me in WhatsApp. I will also put my new number, guys. Okay, 1 second. 54619. The WhatsApp number, what old is there, that is not active, very less active. This is my new number. You can take this and you can, I'm available here in WhatsApp or in LinkedIn, anywhere. If you suffer with any doubts or you have any interview or you're confused, you can ping me. I will respond to you. I may take delay a little bit here and there based on my schedule and work, but I will definitely reach out and help you guys. Okay. So that's all from my
Yeah,
side, guys, with all the
Malik
classes. I
and
hope you have enjoyed the learning. I extended half an hour more today because today's last class. I wanted to recap everything. Okay. I hope you have got the entire idea of deep learning and approach, why we do it. Okay. And remember everything like a story, connect the dots one by one, step by step. That will be easy for you to enjoy and easy for you to remember and recall also. Right? Even in future, when you learn Gen AI, NLP, try to connect the dots, everything from deep learning, what we have learned. Okay.
Thank you so much, Manika.
Yeah, any
The
doubts,
session was
questions,
super,
anyone?
interactive
Now,
and it was very helpful. Manika. Right on.
overall, was it a very fun kind of learning, guys? Did you enjoy learning deep learning?
yeah, actually,
Session was
Manikan, like it was all your sessions were really very, very
Okay,
good.
no response
Like,
means what was it difficult or
no, like no,
Manika,
really,
can
are
you
you
hear
able
me?
to
it
hear us?
was.
Hello?
You explained
Can
it,
you
you
hear?
connected it very well actually.
Okay, I'm not able to hear anyone. Okay. No, I'm not able to hear. Okay.
can you hear now?
Yeah, I can hear now.
Yeah, all your sessions were really very, very good. Please keep teaching more and more. Because
Definitely.
not like finding a good tutor is really very rare. Because like before you, like we got a tutor. He was from Microsoft actually.
Okay.
Not to say wrong of him, but no, like we were not satisfied. But the way you
Okay.
teach, even little kid can understand. This PCA and all, no,
Okay.
like it was so explanatory. So please keep
Yes.
teaching more and more, so many would
Definitely.
be benefited.
Thanks a lot. Definitely. So the main idea is to understand why we are doing it, the necessity of it,
Yeah,
the
that
concept.
basic concept, no, like the
Yes.
bases were really very, very strong.
Yeah. If we simplify anything and we relate it to most simple task we do in day-to-day life, we will connect it very easily.
Yeah,
We can,
every concepts are really very
right.
explained very good. No, like it is
Thank
not
you.
like it is
Yeah.
not you have that magic. So please keep
Thank you. Yeah, I will
sharing
I
knowledge.
request
That's
definitely. I request all of you also to explain to somebody, to old people or children. Try to explain. When you understand everything properly, clearly, you can simplify and explain to anyone in your own language, in your own simple words, in your own examples. When you reach there, which means you understood most of the topics clearly, because we dealt with all complex topic, guys. Adam optimizer, RMS prop optimizer. These are not very school level calculus, right? School level calculus is only chain rule. From chain rule, we connected and we learned the complex optimization functions, which are part of master's level actually. Master's level. But we learned it in we simplified it and we learned it. So I would say you guys also picked up very well, because these optimizers, deep learning, people still struggle. They still can't explain autoencoder why it is non-linear, and PCA why, how you are getting the final values, how you are getting. It's directly there. When you know, you can explain it. Okay, so
Thank you so
that's
much,
very good.
Manikant.
all credits to you. Okay.
Thank you.
And also, like you said, you would give a project.
Yeah,
for
I will.
testing.
Sure. I will add that in this one drive, and I will let you guys know. Also, I have started a Telegram channel, guys. I conducted a session recently at Vasavi University. People liked it and asked to open a Telegram channel. If you want, I will add you guys. I will keep updating some concepts and what is happening in Gen AI space. So let me show you. I will send you the link. If you guys are interested, you can join that. It's my personal thing. Okay. So it's just to have a community active and keep updated, have the continuous learning going on. With that point of view, I've created this. It's just around 20 members so far, but I will keep adding more and more. I'll keep giving more and more information. It will be useful for your career next step, how to grow to the next step and everything. So it will be little slow initially, but you can see it will be active more and more, guys. Okay. Yeah. Yeah, project
Thank you so
definitely.
much, Manikant. Your session
Sure,
was
sure,
really
sure,
helpful.
sure. Anytime, definitely.
Yeah. Regarding the projects, definitely, please
I
let
will
us know.
definitely, I will add it. I'll
Hmm.
definitely add it. Okay. I'll also post final about in the LinkedIn. I'll post about this class. So whoever is interested can actually like it or repost it. You know, if you really found it useful, you can do it. Nothing compulsion, but just in case you liked it, you can comment anything on that. Okay. So already you are connected. I think some of you are connected to my LinkedIn. You can see when my post will come. You can just see it. Right. Any other questions? Any doubts? My Telegram is already there. WhatsApp new is there, old is there. You LinkedIn also, you guys are connected. You can approach me. If you have interviews before that, approach me. You just see what kind of job description it is. Accordingly, you prepare, and you can approach me, and I will help you guys with whatever best is possible at that time. Okay. Great. Okay,
Are you
guys.
mentoring here at Tutort, Manikant?
No. I'm
Okay.
not. I can do that if required, but as of now, no.
So thank you so much, sir. The concepts were very clear, and we were like afraid of deep learning. Like after this, like giving examples, it was very clear. Thank you.
Sure.
So I
Yeah.
think like we need to practice a lot.
Yes,
Get.
you have to because we will forget everything easily. See, even though I am teaching many times, even I forget 2, 3 concepts, right? So it will happen because we are reading a lot, we are digesting a lot. So what we learned 3, 4 months, it's natural to forget. So you write notes on your own language, you keep revising again and again. That's the best thing you can do, right? So you have to do that.
So one more question is like you are building this all these chatbots and LSTM
Mm.
models, right? So are you like implementing it in the, I mean, like pushing through the pipeline and like putting it in the cloud? Is that necessary,
Yeah.
or like
Yeah.
just building it is enough?
No. Yeah, finally, whatever we build, it should be used, maintained, and updated regularly, right? So to use it and make it available to public or many people, cloud is currently the only way, because in the cloud only we have the GPUs support to fine tune any model, any LLM you take like GPT 3.5, whatever. To use it also, you need the Azure or GCP cloud environment. Okay, and then in that you can again fine tune, or you can use RAG approach to build a chatbot. So every code, all the code, final deployment will be in the cloud environment, right? And you have to create endpoints from the cloud environment, which any user can access, right? With some API call or whatever. Internal software engineering will be there through API calls, integration of different components, and initial POC you can build on your local machine on Google Colab, let's say. But final production level will be always be in the cloud environment.
Okay. So to initially get started with some internships or something, like kindly guide us on that. Yeah.
Sure. Okay. Sure. Whatever comes with my through me, I will just share it across in the Telegram group. You can, if you're interested, you can work on it and let me know.
Yeah, sure. Thank you, sir.
Sure. Yeah. All right. Okay, guys. Then that's all
for your
from me from my
explanation,
side. Thank
Nikon,
you.
just one question.
Yeah. Yes.
So, what is the best, like we have Medium articles and Tour data science and other open source
Mm-hmm.
information. So, which is the best one to follow for all these deep learning concepts?
Yeah, so I will type some. Analytics India magazine is good. Analytics Vidya is good. These are free. Medium is very good, but it is paid. Medium is very good, but it is paid. Otherwise, apart from all these, what you can do is in LinkedIn, follow Hugging Face. Hugging Face, as you know, package, right? They have their own company account also in LinkedIn. Hugging Face, Llama Index, LangChain. Okay, and you have this thing for Gemini also. Gemini, Google Gemini is there, right? And OpenAI. All these are there in LinkedIn, right? You follow these pages in LinkedIn. I just typed this, some spelling mistake is there, please ignore that. LangChain, go to LinkedIn and search for these and follow them. So they regularly post articles about industry level use cases and updates what they are doing in every approach. So that way you can learn from them directly. So what many people from Medium, write in Medium, they also first see what is happening in LangChain, Llama Index, Hugging Face, also TensorFlow. TensorFlow 2.0 came now. TensorFlow 2.0 came. They will see many things from here and they will write their own things and I will put it in Medium. Of course, many people do their own analysis and put it in Medium. That's also good. You follow that, but always follow all of these packages you're using, companies you're using, Microsoft you're using, Azure you're using, GCP you're using, AWS, Bedrock, everything you use. So try to find them and follow them. Automatically, you will get to know about the recent updates, but you will be overwhelmed with many information. So go slowly, one by one. You can go slowly. Instead of dealing with 3 cloud environments, deal with only 1 or 2. You don't have to learn GCP, AWS, Azure, everything. Stick with Azure initially. And then after 6 months or 4 months, you go to GCP also, you will automatically relate very easily. You will connect the dots easily and learn it. So you can do this. And one more is for prompt engineering, I will tell. Prompt engineering, one second. There is prompt. The name is, let me type the URL directly. Okay, prompt engineering is anyway not there for you because it comes under Gen AI, but still, I will just put, it's very, very useful. Prompt, yeah, prompting guide. This is useful for prompt engineering. If you read now, you may not understand everything because actually you should learn about BERT model, encoder decoder model, which is all Gen AI. It's not under deep learning. It is next step, Gen AI. You start with basics like BERT, BART, then LLMs, then you go for prompt engineering. But still, I've added this. You can just see if you want. Okay. Yeah. Yes. Okay. Anything else, guys? Okay. Anything else? If you want to ask, you can ask directly in the Telegram or WhatsApp group. I'll always be there to help you. Okay. Yeah. Great. Thank you, guys. Thank you. All the best, everyone. All the best. Thank you, guys. Bye.
Thanks,
Bye.
Monica.
Thanks.